Hi, this is Greg. Welcome to part 3 of our inventory series of videos. This time we're talking about economic order quantity, the quantity that answers the question, how much should we order? So from our last presentation, we talked about the decisions in inventory management, the when, the how many, the where, and the value-added state. This time around, we're just going to focus on that how many question. So when we decide to place an order, when it's triggered, we'll get to that in the next video. How many of those items should we purchase? All right, so here's a sample problem we're going to work through to see if we can get to the solution. So in this problem, a distributor purchases industrial HEPA air filters from a supplier and they buy them for $50 each. And then we have some information about the situation here. So the demand that the distributor experiences, that means their customers, about 60 filters a week. Ordering cost, it costs the distributor $60 to process the order. Remember, that was all the costs around managing the purchase order and receiving, etc. The holding cost the distributor uses to charge inventory is 30% per year. The desired cycle service level is 80%. That means for each service period, each ordering period, that the distributor would like to have product in stock 80% of the time, given what demand might look like. Costs the distributor $50 to buy. We know that already. The lead time is 2 weeks for the product, and then the standard deviation of weekly demand is 10 filters. So we have a little variability of demand. Okay, the objective overall for the problem is to determine the inventory policy. That is the answer to the two questions, the when and the how much. This time we're just going to be talking again about the how much to order. So the economic order quantity is our objective. And at the bottom there you can see that the EOQ is actually identified by a guy named Harris back in the early part of the 1910s. And he was an engineer who was high school trained, ended up with 70 publications in journals, and ended up being a lawyer later in his life in California, so quite remarkable. And then about 20 years later, Wilson wrote this article in Harvard Business Review, and Wilson gets a lot of credit for publicizing this routine, but even though it was Harris who may have derived it all. So we need some variables to help us solve this problem. In some terminology here. So for EOQ, economic order quantity, we need to know the annual demand. And remember, in the problem, we were given period demand. That's the small d. Annual d, or annual demand is a capital D. The setup or ordering costs, and I've grayed out, by the way, the small d, because while it was a variable provided in the problem, we don't need it for the EOQ solution. So the setup costs we need, or ordering costs. We have to know the inventory carrying cost rate. That's the 30% from our problem. We need to know the cost of the product that we have to buy. And then ultimately we're calculating Q star, the EOQ. So knowing those variables, and here's the data from the problem again, we're going to gray out everything that only applies to reorder points. So we're left then with period demand, the ordering cost, the holding cost rate, and product cost. The other things are appropriate for ROP, but not for EOQ. Let's keep moving. So here's the derivation of EOQ, and I'm going to ask you to remember your calculus here. So we're looking for the Q, the quantity that minimizes total annual costs from this formula. So the total cost we're trying to minimize for a product would be its associated annual ordering costs, its associated annual holding costs, and the associated annual purchase costs, so the amount they'd have to buy for the entire year's worth of demand. So you can see these are identified in the equation then. Total cost is equal to the cost to place an order, that's S, times the number of times we order per year. And the way we calculate that is annual demand divided by how many we buy from the supplier at a time will tell us how many times we place an order times the cost of that order. That's the ordering cost. Holding cost is the average inventory value over time, and again, through calculus, we can get to that a derivation of that to be Q over 2 times the rate, the cost to carry 1 unit for 1 year. So it's the rate is 30% times the cost of the product. That's going to show up to be $15 in our example. And then the total annual cost to buy. So if we put in our, or to get to Q star, then what we do is we have to find the, or have to take the first derivative of the total cost with respect to Q, and then set that to 0 and solve it, and then we'll see what we get. So as we do that, to set that to 0 and solve for Q, you can see that the last term goes away. The DC term goes away in this taking the first derivative because there's no Q in that term. So it actually goes to 0, and that's what I mean by going away. So if we solve this thing for Q, here's the answer. Q star equals the square root of 2ds divided by IC. So that's 2, that's the capital D, annual demand, times the cost to place an order, divided by the cost to hold 1 unit for 1 year, and that's IC. So we're going to use this Q star equals the square root of 2ds over IC to calculate the EOQ. So for any situation, here's more of this derivation. If we bought just one at a time, our holding cost for that product would be very low. We wouldn't have to hold any in inventory. We're just buying exactly what we need. At the other end of the scale, we would be buying the entire year's worth at once. So our holding costs then would be relatively high. Relative to that ordering cost, if we had to buy one at a time, our ordering cost would be quite high. We'd be placing a lot of orders. On the other end of that, though, if we only placed one order for the year, our ordering costs would be low. So we want to average or add those two things together and come up with total costs. We could also add into there the product cost, but those are stable in the assumptions of EOQ. We'll talk about that in a second. And then we have total costs, and we're looking for then the Q, the quantity that will minimize the total cost. You see then Q star shows up at some level, and it is the bottom of that total cost curve. All right, so and one other thing to note here, very importantly, is that the bottom of the total cost curve, the cost minimum, is the point at which holding costs and ordering costs are equal. So really Q star is looking for this balance between the cost to hold the inventory versus the cost to place orders. And when we can get those things balanced, that's going to be the right number, the number that will minimize total costs. All right, so some assumptions that Harris identified in formulating his solution to this problem. Demand is known and constant. That means it never changes, and you know exactly what it is. Everything that you build or order arrives instantaneously. Single delivery, no lot splitting, so it all arrives, it all shows up. Costs to order or set up are constant and known. You're not allowed to have back orders, and there are no quantity discounts in place. So I would say very few of you would say, oh, that describes my business perfectly. In fact, none of you would describe that as or identify those as characteristics of your business. It just doesn't work that way. So there are workarounds for some of these, that we relax these assumptions and constraints. We're not going to go through those here. Probably the most common one is quantity discounts, and there's a quite simple extension of EOQ to accommodate the quantity discounts. We're not going to do that in this video. So here's again the solution for our situation here. The Q star is where the holding costs and the ordering costs are the same, the point at which they cross, and we see that's going to be 158. We derive that using the formula square root of 2ds over RC. Now, importantly here, the capital D again is annual demand. So in the blue box there on the bottom left, D is equal to 3,120. That is the demand per week, which was 60 times the number of weeks in a year, 52, and that's where we get the 3,120. The other 60, the S, is the cost to place one order. I is the carrying cost rate, and then C is the cost to buy a product. So if we solve that, we get 158, and if we put that into our total cost equation, then the total cost is going to be 158,370. Now the bulk of that is from the product cost. That's the DC term is actually equal to 156,000. The cost to order and hold turn out to be what, $2,370 in that point. So again, I made a note there in the bottom that the D here is annual demand, not the small d, not period level demand. Okay, so just to wrap this up, here's a reprint of Harris's article from 1913. Gosh, 100 years ago nearly, this was put out. So yes, we're teaching you and talking about 100-year-old formulas. However, given all those crazy assumptions around EOQ, it is still widely used in many many ERP and computerized inventory management situations. But you can see that curve that Harris included in his article is just the same. We have setup costs, we have holding costs, we have the total cost that is adding those together, and we're trying to find the EOQ that minimizes those. And you can see his 6850 is the quantity that's going to show up right here below, next to the 7. So right about on that line is where the total costs are going to be minimized. That looks a lot like this that I pulled off of an older Excel graph of our solution. One thing to note here, the reason that EOQ is used a lot is check out how flat this total cost curve is. Even if we don't know exactly what the rates are or the variability might be, that anything we pick along this line is actually our total costs are going to be about the same. They're not going to change very much. And the reason that's true is because of the square root term in the EOQ. It dampens out errors in assumptions or errors in the actual rates, let's say, to carry inventory. And finally, yes, there's an app for that. As I was looking around for stuff recently, I came across this. There is a brand new EOQ calculator app for Android. You can buy it for $1.58. What's a crazy number to have as a price? But there you go. So that's the answering the question: how much should we order? The next video we'll look at will be to help us determine the when question, the reorder point that will trigger the release of an order. All for now. Thanks.